In this video, we're going to expand a little bit upon Chapter 3 and start talking about molecules in 3 dimensions. So this first video is going to be on the concept of chirality. So as we've seen before, stereochemistry as a concept is all about the 3-dimensional shape of molecules. We know that molecules do not exist in 2 dimensions. They have electron clouds, they have bonds sticking out in multiple different directions. In Vesper theory or in Gen Chem, you saw that there's different shapes to molecules. So stereochemistry is kind of understanding that molecules have 3-dimensional shapes. Now in organic chemistry, we have a couple concepts to describe this. Our first concept is called chirality, or being chiral. So the concept of chirality says that when a molecule is chiral, you have mirror images of a molecule. Say you put it next to a mirror plane, and when you take them next to each other, they are not superimposable. So what that means is when I take a mirror plane and I put it next to a molecule, and I take the mirror image of it, there's no way I can twist and bend and rotate that molecule such that it can go upon the original one. Now, we are familiar with chiral images in real life, so drawings are chiral, hands are chiral, bodies are chiral, block letters, if they're in 3 dimensions, are chiral. Things that when I take a mirror image of it, it cannot be put on the original image. Now, the opposite of chiral is achiral. If chiral means the mirror images are non-superimposable, achiral means the mirror images are superimposable. So this is things like mugs, or pencils, or cups, or plates. Anything that when I take a mirror image of it, it is going to be superimposable on itself. I can rotate it around, and it will have a superimposable mirror image. So what does this look like in organic chemistry? So a chiral carbon is going to have 4 unique substituents or groups around it. So what that means is if we look at an example, say we have CH4, and I'm going to draw that with wedge and dash bond, so it looks like it's 3D. CH4 has 4 different hydrogens around it. They are all the same. So this would be an example of an achiral molecule. Something where we have CH2, say we have 2 H's, and then we have a Cl and a Br. We have 3 different groups around it, right? We have a bromine, we have a chlorine, but then we have 2 hydrogens around it. So we don't have 4 unique substituents, so this would also be achiral, and we'll see in a later video why this is the case. However, if we have a carbon, say it has a chlorine, and has a bromine, and it has a hydrogen, and it has a CH3, we have 4 unique substituents around this carbon in the center. So we would call this carbon chiral. This would be a chiral carbon. Sometimes it's given with carbon with a star next to it. If we're examining this in molecules, we can draw out different molecules and examine for chiral centers. So say I have this molecule here. I'm going to put a Cl here. And remember, there's an implicit H going back. If we look, we have a chlorine, we have a hydrogen, we have an ethyl group, and we have a propyl group. So this carbon here we would call chiral because it's got 4 different groups around it. Now if we shifted this over to something like this, and I put a Cl here and I had another hydrogen back here, we have the Cl, we have the hydrogen, but then we have 2 ethyl groups that are exactly the same as one another. So this would not be a chiral center. In fact, this would be an achiral molecule. But in this case, this would not be a chiral center. We can do this with cyclic structures as well. So for instance, say I have this structure here, and I'm going to put a methyl, and I'm going to put an OH. Remember that each of these points has an implicit hydrogen. Say I want to examine this carbon here and determine if it's chiral. So we look, we have an OH, we have an H. And if we're examining around the ring, we see that this direction around the ring is slightly different than this direction around the ring. In this case, we have a methyl group on this side, but no methyl on this side. So since the directions around the ring are different, we would indeed call this carbon chiral. And if you're examining this structure, you would see that this carbon is also chiral. So we'd have both of these would be chiral carbons, and would include chiral points throughout the molecule. What we notice about is that achiral molecules, such as this one and this one, are all going to have planes of symmetry. So if we look at this molecule here, we can see that we can draw a plane of symmetry through the hydrogens. So these two H's are in the plane of symmetry, and the Cl is pointing out, this Br is pointing back through it. I'm sorry, this is not, we can see that these hydrogens are in the same plane. So what we do is we can say that if we take a plane and put these bromines in the plane, we can see that these hydrogens are reflected across from one another. So we would see that this has a plane of symmetry in it, and we would say that that's an achiral molecule. Something like this structure here, say I have an OH, say I didn't put that methyl group down here, but I just had an OH. We can draw a plane of symmetry right through the center of the molecule, and that would be indicating a plane of symmetry. So this would be an achiral molecule. Just to knock this point home, if we, for instance, had this type of structure here, we can see that neither this nor this are chiral points, and indeed we can see the plane of symmetry right through the center of the molecule. So neither of these would be chiral. These would both be achiral molecules. Then these would not be chiral centers. They're indicated with the wedge and dash bonds. The final portion of this we see that chiral molecules have optical activity. So by having optical activity, that means that this is going to rotate. It rotates plane polarized light, and it's going to rotate it left or right, depending on what type of chiral center we have. So chiral molecules have optical activity. We also see that if we have a mix of chiral molecules, one must be in excess, and this is sometimes called enantiomeric excess or %EE. The number that is given to this quantity is called specific rotation, and this is sometimes given the letter alpha sub D. And specific rotation is going to be some number of degrees left or right, and this is telling us how much the light rotates. So every chiral molecule has a specific rotation. This is something you look up. It's not something you could ever predict. It's experimentally determined. And it's going to be either D or L, dextrorotary or levorotary, depending on whether it rotates D left or right. If you have a mixture of enantiomers or a mixture of chiral molecules, this specific rotation is going to be a weighted average of the individual enantiomers. So you would have your specific rotation of one enantiomer times the percent plus the specific rotation of the other enantiomer plus the percent. If these are enantiomers, and we'll get into what that means in a later video, one of these would be positive and one of these would be negative. But this would give us, depending on the percentages that you get here, the mixture, then you would get a alpha D that's different. You can see here, if this is 50-50, and this is plus 9 degrees and this is minus 9 degrees, you'll see that your specific rotation ends up being 0 degrees, which is why one must be in excess. If you have a mixture of chiral molecules, if it's 50-50, then you're going to have a zero optical activity, and you will observe no optical activity and no specific rotation.